Hello everyone, welcome back to my YouTube channel. In this particular video, we'll be looking into SVM, that is Support Vector Machine. We are going to look into every single mathematical intuition in detail in this particular video. Trust me, the mathematics behind Support Vector Machine is very much confusing. But I have came up with this one short video which will clear all your doubts related to the mathematical intuition, equations as well as everything related to support vector machine. So first, let's have an overview of what support vector machine is. It is basically a supervised machine learning algorithm for classification and regression. Supervised machine learning algorithm means those algorithm which works for labeled data. Here, along with the features of dataset, we also require the output labels for that particular data point so that it can be used for training and making the model. So this is what supervised machine learning algorithm is. And in this particular supervised machine learning algorithm, we have two types, which is classification and regression. For both the types, the support vector machine is used. Majorly for classification, it proves to be the best. Now the beauty of support vector machine is that it can handle high dimensional data or non-linear data. High dimensional data means the data contains more number of features as compared to the number of observations. So in that case also, support vector machine proves to be the best. Now there is a drawback of support vector machine. It is that it is not suitable for large datasets because it is computationally very much expensive, that it cannot be able to handle extremely large dataset because it requires certain time for performing all its iterations, as well as it requires large amount of resources. Hence, it is not that suitable for larger datasets, but it works well for small to medium sized dataset. It is going to provide the most accurate answer with these kind of datasets. Now, the support vector machines can handle binary as well as multi-class classification problems, but SVM gives best results on binary dataset. It does not give that best result for a multi-class classification problem, but when it comes to binary classes, it gives the best results. It is widely used in various domains, for example, image recognition, finance, and many other domains in machine learning as well as deep learning. So I hope you might have got an overview of what exactly support vector machine is and what it is used for. Now we will look into a detailed scenario of support vector machine and its working. So let's see what exactly it is and how it is used for classification problems. So let's consider this particular axis. Here you can see we have x-axis and y-axis, and onto this we have one class. Here you can see we have one class of triangles, and similarly we have some other class of circles. Now these classes are oriented in some manner, and you can see all similar data points are close to each other. Now these two classes has to be separated, so it is separated by a separation line. This particular line separates the classes from each other, and what this particular line is called as, in support vector machine, this particular line of separation is called as hyperplane. Yes, hyperplane is the line which separates the two classes in binary classification. Now obviously this line of separation cannot be drawn randomly. We'll have to look how it can be drawn or what are the certain constraints to draw it. So first let's see the equation of hyperplane. So you can see that the equation is given as W transpose multiplied by x plus b equals to 0. Now there are a lot of terms in this equation. We do not know what they are actually. So let's see all these terms one by one, starting with W transpose. So it is nothing but a vector that is perpendicular to this hyperplane. Just imagine a vector which is perpendicular to the hyperplane, and it also defines the orientation as well as the direction of the hyperplane. Hyperplane is also called as decision boundary. It is also called as the coefficients of the variables that are included in a particular problem. You can see that it is acting as a coefficient of x. Now as I said, it defines the orientation of the hyperplane. You can see that the orientation can be defined by rotating the hyperplane to what extent we need to rotate the hyperplane such that it perfectly separates the two classes. You can see this is how it adjusts itself with this particular parameter W transpose. So I hope the significance of W transpose is clear to some extent. Now let's move on to the next term, which is X. So in this particular hyperplane equation, X is nothing but the variable. X in SVM refers to an input feature vector or the data point containing the values of individual features that describes a specific data instance. That means, as I said, there are data points, and since these data points are oriented, it is going to have certain coordinates, and those coordinates are signified by this variable X. We will see an example which will clear all your doubts. Now the next term is B. B refers to the bias term. It is also called as intercept, which helps in positioning the decision boundary, which means the hyperplane, accurately. Now once we have defined the orientation of hyperplane by rotating it, we also need to adjust it to perfectly separate the two classes. So it can be adjusted with the help of the bias term. You can see how it is adjusted. So this positioning has some value, and that value will be stored in the bias. So I hope the bias term is also clear. Support vector machine has to find out the perfect hyperplane by adjusting all these parameters. So I hope it is clear. Now we'll see an example which will signify all these terms in detail. Let's say we have these two classes, and these two classes are oriented with reference to the x and y axis in such a manner. Now you can see that we have drawn a hyperplane. Again, this hyperplane cuts the x and y axis at certain points. You can see that the horizontal one is x axis and the vertical one is y axis. So on the x axis, we can see this hyperplane cuts at the coordinate 2, 0, and at the y-axis the hyperplane cuts it at the coordinate 0, 4. So we have got these two coordinates, and with the help of these two coordinates we can find out the slope of this particular hyperplane by the formula y2 minus y1 divided by x2 minus x1. If you are not aware of how to calculate slope, then don't worry, let's say that slope is also given to you in the question. So slope is minus 2, and the intercept of this particular hyperplane, which is denoted by c, is nothing but 4. Now we are aware that the equation of any line is nothing but y equals to mx plus c, where m is slope and c is the intercept. So if we plug in the values of slope and intercept in this particular equation of line, we'll get the equation y equals to minus 2x plus 4. So I hope the equation of hyperplane in this particular scenario is clear to you all. Now let's consider this particular data point from the class of circles. The coordinates of this particular data point is 5, 5, which is next to the hyperplane. We already have this particular equation y equals to minus 2x plus 4. We know that the standard form of hyperplane equation is w transpose multiplied by x plus b equals to 0. Now we need to rearrange this particular equation y equals to minus 2x plus 4 in this particular hyperplane equation form. So we can get the equation as 2x plus 4. We can just shift this minus 2x plus 4 on the left hand side. We'll get plus 2x plus y minus 4 equals to 0. Now whatever equation that we have got, if you compare it with the standard form of the hyperplane equation, we can clearly see that w transpose is nothing but 2, 1. Now why 2, 1? Because it is already said that it defines the coefficient of all the variables. Here we have two variables x and y. The coefficient of variable x is 2 and the coefficient of variable y is 1. Hence 2, 1 is the w transpose. And you can clearly see that b is nothing but the bias term, which is minus 4 in the equation. Now as I said, we have to consider this particular data point of the coordinate 5, 5. This represents the x term in the equation w transpose multiplied by x plus b. So we have got the x, we have got wt, we have got b. Let's plug in all these values in the expression w transpose multiplied by x plus b. Now in W transpose we have two values 2, 1 as well as in X we have two values 5, 5. So how to multiply them? We have to multiply each and every term by considering its index. So you can see that we have the first term as 2 and the first term as 5. So 2 multiplied by 5 plus the second term is W transpose is 1 and the second term in X is 5. So 1 into 5 plus the bias term which is minus 4. So when you compute this you will get 11 as the answer, and you can see that the sign of 11 is positive. Hence it states that this particular data point lies in the positive class. Similarly, if we take one more data point from the same class, the coordinate of this data point is 3, 2. So let's check whether 3, 2 is giving us positive answer or not. So again you have to define the same expression W transpose multiplied by X plus B. Here W transpose is 2, 1 and X is 3, 2. You have to multiply each term by considering its index. So first term 2 and 3 will be multiplied plus 1 and 2 will be multiplied plus the bias term is minus 4, and after computation we get the answer as 4, which is again positive. Similarly, if we take any other data point from this particular class of circles, it is going to always give the positive answer when all the values are plugged in the expression of hyperplane. So similarly, we'll now test it for the data points which lies in the class of triangles. So let's consider this particular triangle data point which has the coordinate minus 3, 0.5. So in this particular case, our X will be minus 3, 0.5. Now we need to consider the same expression W transpose multiplied by X plus B. You can see W transpose first term is 2 and X first term is minus 3. So 2 multiplied by minus 3 plus second term in W transpose is 1. Second term in X is 0.5. So 1 multiplied by 0.5, and next is the bias term which is minus 4. So when you compute all this you will get minus 9.5 as the answer, which is negative. Similarly, if you consider one more data point from the same class of triangles, let's say this particular data point has the coordinate 0.1, minus 4. We'll consider now this as X. So let's say X is 0.1, minus 4. So similarly, if we compute the value by plugging in all the values in the expression W transpose multiplied by X plus B, we will get the answer after computation as minus 7.8, which is again negative. Similarly, if you take any other data point from the class of triangle, you will always get negative answer. And that is why this particular class is called as negative class. So I hope these two classes are clear. So just remember that the blue circles are positive class and the yellow triangles are negative class, based on the hyperplane that we have considered in this particular case. So I hope now you can relate that how this hyperplane is helpful in categorizing the data points in two different classes. So up till now whatever we have seen, logistic regression also follows the similar kind of rule for classifying the binary classes. So what makes support vector machine different from logistic regression? We will now see it by looking at its working. So let's say we have this line of separation called as hyperplane with this particular equation. We have the positive class as circles and the negative class as triangles, which we have seen in the previous example. We have already proved that. Now once the hyperplane is drawn, in support vector machine, data points from both the classes which are closest to the hyperplane are found out. So you can see these two triangles from the class of triangles are the data points that are closest to the hyperplane, and similarly from the class of circles, this one single data point from the class of circle is the closest to the hyperplane. And what these points are actually called as, these are called as support vectors. So I hope the definition of support vector is clear to you all. These are nothing but the data points that are closest to the hyperplane from both the classes. Now once we find out the support vector, a line is drawn from that support vector which is parallel to the hyperplane. So here you can see that we have drawn two lines which is parallel to the hyperplane passing through the support vectors from both the classes. This particular lines which passes through the support vectors and is parallel to the hyperplane is called as support vector line or gutters. The line which is passing through the support vector which lies in the positive class is called as positive gutter, and the negative class line is called as negative gutter. Now let's consider the distance between the negative gutter and the hyperplane as d1. Similarly, the distance between the positive gutter and the hyperplane is d2. and the distance between both the gutters is called as margin. You can see that margin is nothing but the summation of these two distances d1 and d2. Now, this margin distance plays a very important role in the support vector machine algorithm. Let's see what is the goal of support vector machine. So basically the goal of support vector machine is to draw a perfect hyperplane. Yes, you just cannot randomly draw a hyperplane which separates two different classes. There is a certain rule for drawing the perfect hyperplane, and once the perfect hyperplane is drawn, then only that will be called as a generalized and an optimized model. So you can see this was the previous hyperplane that we have drawn. Now let's shift this particular hyperplane to some extent. Let's slant it more. This is the new hyperplane. You can see the difference. The previous one was looking something like this, and now after manipulating the parameters such as bias as well as the W transpose, it is looking something like this. So let's draw the support vectors for this particular hyperplane that is newly drawn, and let's draw the gutters also which are passing through this support vector. And also let's try to calculate the margin distance for this particular scenario. Now we have calculated the second margin distance for this particular scenario. Now let's compare the two cases. In the first case, the hyperplane was something like this and the margin distance was this one, and in the second case we have slanted the hyperplane and the margin distance is this. So if we compare these two, we can clearly see that the margin distance in the first case is very much smaller than the margin distance in the second case. And this we got by just adjusting the parameters of W transpose as well as bias term. Now the goal was to draw a perfect hyperplane, and in support vector machine this can be achieved by maximizing the margin distance. So if you remember, in the comparison we have seen margin 1 was very less than margin 2. So when the model will be created in the second case where the margin was more, that particular model will be the best and will give the best result. So this goal of drawing the perfect hyperplane is achieved by maximizing the margin distance, and that is what the support vector machine is. It finds the best hyperplane in such a manner that the margin distance, that is the distance between both the classes support vector, is the maximum. Now let's take the second case where we have got the margin distance higher than the previous one. Now the equation of the positive gutter is given as W transpose plus X plus B equals to 1. Now why 1? Because this is towards the positive class. Therefore it will be positive 1 to the RHS of this particular equation. And similarly the equation of the negative gutter will be W transpose plus X plus B equals to minus 1. Now why minus 1? Because this particular gutter is of the negative class, therefore the sign here is negative. So by this particular equations, I am damn sure that you might have got confused and there might be many questions regarding this particular equation. Basically you might be having these questions that why we have taken 1 and minus 1 in the right hand side, why not we have taken 1 and any other number, let's say minus 24, and why we have not taken 3 and minus 3 instead of 1 and minus 1. So let me first answer the question 1 and 2. We haven't taken 1 and minus 24, that means the different magnitudes, because in support vector machine it is mandatory that the distance between positive gutter to the hyperplane and the distance between negative gutter to the hyperplane, both these distances has to be same. If these distances are same, then only your model will be perfect. Just imagine if d1 is greater than d2, then you are giving more weightage to the negative class, and this will be injustice. Therefore, for a perfect SVM model, these two distances d1 and d2 must be equal. Therefore, for the equations I have taken the same magnitude 1 on the right hand side of both the equations. Now let me try to answer the third question, that instead of 1 as a magnitude, why I haven't taken any other magnitude? Why not 3 or minus 3 in the two equations? So this is done just to avoid calculation complexity. If you take any other number rather than 1, it will be little difficult for you to calculate because there are a lot of equations that are contained in support vector machine. So just to have less complexity in calculation, we'll be taking one. So I hope all your doubts are clear. Now we'll look at the derivation of computing the margin distance. As I said, margin plays a very important role. The more margin is, the better is your model. So therefore, we have to find out the margin first. So let's say we have these two support vectors of both the classes, and we also have drawn the gutters. Let's say that the support vector which comes in the negative class is x1 and the support vector that comes in the positive class, which is nothing but the class of circles, is x2. Now we can easily compute the distance between x2 and x1 by the formula x2 minus x1. As you already know that this data points has coordinates, so by that we can compute the distance between x2 and x1. The goal is to find out the margin. If you carefully observe, this particular margin is strictly perpendicular to the hyperplane as well as both the gutters. Basic idea is to find out the perpendicular distance between both the gutters. We have these points x1 and x2. We also have the equation of the positive gutter, W transpose multiplied by x plus b equals to 1, and for the negative gutter we have W transpose multiplied by x plus b equals to minus 1 because it lies on the negative side. So I hope these two equations are clear. Now the rule says that y of I. What is y of I? It is nothing but the prediction. For any data point which is xi, the y of I is nothing but the prediction in which class it falls. It is mainly dependent on two conditions. The prediction y of I will be positive only when the expression value is greater than or equal to 1. If you remember the previous example where we have calculated the value of this expression for certain data points, it was greater than 1, that means positive for the data points which were falling under the positive class. Similarly, the value of the expression was coming out to be negative, that means less than or equal to minus 1, when the scenario was that the data point was falling under the negative class, that means the yellow ones. So you will get the yi, that means the prediction value for a positive class, as plus 1, and for a negative class you will get the prediction value as minus 1. So if you get plus 1 as the prediction value, the data point will fall under the positive class, otherwise in the negative class. Now we want these two conditions to be a single condition. We can just boil down this particular two conditions into single by just multiplying the prediction value y of I for both the cases. So now for positive case, you can see that we already had the expression W transpose multiplied by x plus b. If you multiply y of I to it, what we will get? In the positive case, we already know that the prediction will be plus 1. So plus 1 will be multiplied with this particular expression, which will be greater than or equal to 1. Now once you multiply anything with 1, the answer will be the same expression only. So here as the answer we have got W transpose multiplied by xi plus b greater than or equal to 1 for the positive case. And now for the negative case, you know this is the condition. Here you can see that the expression is less than or equal to 1 since it is negative. As you know that y of I will be minus 1 for negative class, that means the prediction is going to be minus 1. Now if you multiply minus 1 with the entire equation, what will happen is the sign of less than or equal to will change to greater than or equal to, and minus 1 when multiplied with minus 1 it will get plus 1. If you carefully observe, for both the cases we are getting the same equation. So you can now say that these two conditions of y of I will boil down to a single condition, that is y of I multiplied by the expression will be always greater than or equal to 1, provided that the data point is lying on either side of the gutters. If the data point is lying between the margin area, that means between both the gutters, then the multiplication of y of I and this particular expression will be lesser than 1. But if the data points are lying to the right of the positive and to the left of the negative gutter, then in that case this condition will be true. That means the multiplication of y of I and the expression will be greater than or equal to 1. So I hope how this condition boils down to 1 is clear to you all. We have this particular case of x1 and x2 and we also have the margin. Basically, we have the condition that y of I multiplied by the expression will always be greater than or equal to 1. Now with the help of this particular condition, we'll find out the margin distance. So basically these 2 points x1 and x2 are nothing but vectors. So it will be having certain direction. So let's draw that direction. So you can see that x2 and x1 are having this particular direction. These are nothing but vectors. So now we already know that the distance between x2 and x1 can be calculated by the formula x2 minus x1, because we already have the coordinate points of both these vectors. So let's write that we can compute the distance between x2 and x1 by simply subtracting x1 from x2, since x2 lies in the positive class. Now as this margin is perpendicular distance between both the gutters, we want certain parameter which is perpendicular. If you remember, at first we have seen that Wt is the parameter which is perpendicular to the hyperplane, and this margin distance is also perpendicular to the hyperplane. So this Wt parameter is going to be very much helpful for finding out the margin distance. So basically if we project the x2 minus x1 distance onto this perpendicular Wt vector, then we will get the margin distance easily, and this can be done by simply taking the dot product of x2 minus x1 and the Wt. But here in this case we cannot take Wt as it is, we will have to convert it into unit vector. Wt can be converted into unit vector by simply dividing it by its norm. So we can now compute the margin distance by taking the dot product of x2 minus x1, that is the subtraction of these two vectors, and Wt divided by its norm, which will convert Wt into its unit vector. So when we take the dot product of these two, we'll simply get the margin distance. So I hope how we have computed this particular formula, it is clear to you all. Now if we multiply the Wt term in the numerator to each and every term that is present inside the bracket, we will get x2 dot product W transpose minus x1 dot product W transpose, the whole divided by W norm. Now at this particular point we do not know what is the dot product of x2 and W transpose and x1 and W transpose. So for this we'll have to think a bit different. If you remember, we have the condition for the data points as yi multiplied by the expression W transpose multiplied by x of I plus b will always be greater than or equal to 1. But for support vectors, this condition will boil down to equal to 1. This multiplication of these two terms, that is yi and the expression, will always be equal to 1 because it is actually lying on the gutter. The support vectors are lying on the gutters. That is why it will be equal to 1. So therefore x2 and x1 are also lying on the gutters. So for x2, since it is lying on the positive gutter, prediction for x2, that is yi, will be plus 1 multiplied by the expression W transpose multiplied by, instead of xi we can write x2 plus b equals to 1. We have this condition. If we take W transpose multiplied by x2 on one side and the other terms on the right hand side, we can get W transpose multiplied by x2 equals to 1 minus b. Similarly, we can do it for x1. Since the data point x1 lies on the negative gutter, the prediction yi for it will be minus 1, and if minus 1 will be multiplied with this particular expression, we'll get the expression as W transpose multiplied by x1 equals to minus 1 minus b. We have taken the bias term to the right hand side. Now that we have got the values for W transpose multiplied by x1 as well as W transpose multiplied by x2, we can simply substitute in that particular place. So W transpose multiplied by x2 vector will be 1 minus b minus of minus 1 minus b divided by W norm. So when you compute this, you will get 1 minus b plus 1 plus b divided by W norm. Now you can see that minus b and plus b cancels each other and 1 plus 1 gives you 2. So in the numerator we will be left with 2 and in the denominator we have W norm. So you can see that margin distance is given by the term 2 divided by W norm. This is how we can calculate the margin distance. So I hope the derivation was clear to you all, and I have tried to make all the equations very precise and very clear. I hope there is no doubt. If you have a doubt, then please try to watch that part again, or you can just put your queries in the comment section. So we have finally computed the margin distance. It is given by 2 by W norm. What is our aim? Our aim is to maximize this margin distance. This can be maximized by altering two parameters. One is the W, that is the orientation or the rotation of the hyperplane, if you remember, and second is the bias term, which is nothing but the positioning of the hyperplane. If we alter these two parameters and we get the perfect hyperplane, we can get the maximum margin distance. Now yes, the margin distance can be maximized on a certain condition only, that y of I multiplied by the wt multiplied by xi plus b will always be greater than or equal to 1. That means only for those data points which lie on the right side of the positive gutter and on the left side of the negative gutter. It won't be applicable for a data point which lies between the margin distance, that means between the two gutters, positive and negative gutters. So you can see that this particular case of maximizing the margin is only applicable when you have a perfect scenario, something like this. You have perfectly oriented two different classes which can easily be separated by a hyperplane. But in real world scenario, we cannot have certain situation where the two different classes are perfectly separated from each other, and one single line of separation can separate these two classes. So therefore, this particular condition of maximizing the margin distance is only applicable for a situation like hard margin SVM, where it cannot handle any data point which comes between the two gutters. If any data point comes between the two gutters, it has to adjust the hyperplane again, and that is why it is called as hard margin SVM. So in the upcoming video, we'll be looking into another form of SVM which works best even when your data point comes in between the two gutters. That is nothing but the soft margin SVM. I have done a lot of research for finding out the precise and accurate information for the mathematics behind the SVM. I hope the entire mathematical intuition of SVM is clear to you all, with all the equations as well as examples. Please like, share, subscribe and follow me on Instagram.